Assalamu alaikum, dear students. Today we are going to discuss the second part of the weight volume relationships. In the previous lecture we discussed part 1 in which we developed some relations. Today we are going to discuss the second part of the same lecture. So let's begin. First of all, we have to discuss some additional relationship among the unit weight, porosity and moisture content. As I discussed earlier, the purpose of this lecture is to make you understand the relationship between the properties related to the volume in the weight. So if you know a particular property, particular quantity, you can determine the other properties from that. And this is very important in borrow and fill problem, in compaction problems, in the problem in which we need to determine the dry unit weight, saturated unit weight or bulk unit weight of a particular soil under a particular condition. So usually the unit weights or densities are important and they are calculated from these properties. So we will be discussing relationship to determine these. So now today we are going to discuss the relationship among the unit weight, which is also known as bulk unit weight, porosity and moisture content. So now because we are discussing porosity today, and you know the porosity is basically volume of voids divided by the total volume, while the void ratio was basically equal to volume of void divided by volume of soil solids. So this is there is a small difference between void ratio and porosity. Porosity it's divided by the total volume, void ratio it is divided by volume of soil solids only. Now if we have the same three-phase diagram in which we have solids, its weight of solids and its volume, then we have water and its weight as WW and its volume as volume of water, and then we have air, its weight is 0 and its volume is volume of air, or the total voids which are filled with water and air. If you take them combined, their volume will be equal to volume of voids. So if you add volume of voids and volume of soil solids, that will be the total volume, and if we add the volume of water, weight of water and weight of solids, then that will be the total weight of a sample if we are considering this in a 3 separate phases over here. So now let's consider that we have a volume of soil equal to 1. You've got 1 cubic meter or 1 cubic feet or 1 cubic centimeter of a soil, okay, a unit volume. Okay, so if we consider that the volume of the soil is equal to 1, then obviously we know from this equation that the porosity is equal to volume of voids divided by the total volume, because we have taken total volume is equal to 1. So if we replace this V by 1 in this equation, so volume of voids will be equal to N. Okay, so which you can see over here, and the same thing we will represent this on the figure as well over here. And similarly, because volume of soil solids is the total volume minus volume of voids, so volume of soil solids will be equal to, over here you can have the total volume minus volume of voids. The total volume is equal to 1, volume of voids is equal to N, so you can write V as in this manner. Now coming to the other side of the equation, how to determine the weight of soil solids and weight of water in terms of void ratio, because porosity, because we are determining the relationship with the porosity, so we are converting everything into porosity over here, you can see. So and same applies over here as well. So now coming to the weight side. Now first of all, let's determine relationship for between the porosity and weight of the soil solids. Now we know that specific gravity is equal to unit weight of soil solids divided by unit weight of water. Now unit weight of soil solids is basically equal to weight of soil solids divided by volume of soil solids. Okay, so just replacing this with its representation in terms of Ws divided by Vs. Now further simplifying this equation, and keeping Ws on left hand side while taking Vs and gamma W on the right hand side of the equation here over here with the Gs. This can be rewritten as Ws is equal to Vs into Gs into gamma W. So now as we know that the Vs over here is equal to 1 minus n. You can see over here Vs is 1 minus n. So replacing the value of Vs in this equation as 1 minus n from this Vs, we get Ws is equal to Gs gamma W into Vs is replaced with 1 minus n. So Ws is equal to Gs into gamma W into 1 minus n. So the weight of the soil solids can be determined in terms of void ratio and specific gravity and unit weight of water using this relationship. So unit weight of water is constant, Gs is constant for given soil. So if you know the void ratio, you can determine the weight of soil solids. Similarly, for weight of water, we know that the moisture content of a given soil, small w, that is equal to weight of water divided by volume of soil solids. Now weight of water, because we want to determine weight of water over here, so weight of water will be equal to moisture content into Ws, which is weight of soil solids. We already determined Ws over here, so we will just simply put the value of Ws in this equation. So weight of the water will be equal to moisture contents times Gs times gamma W into 1 minus n. So this is the weight of the water. So we can write the weight of water in terms of the porosity and specific gravity, moisture content and unit weight in the following form. So now we have converted everything in the porosity, you can see over here. So let's moving on and determine some further relationships for dry, bulk and saturated unit weight. Usually we want these three different types of unit weights for a particular soil. Either we have one or we want to determine another. So first of all, deriving correlation or relationship for dry unit weight. Now you know that the dry unit weight is equal to weight of soil solids divided by the total volume. Alright, so now replacing the values over here, you know Ws as we determined on the previous slide, weight of soil solids, that is equal to Gs into gamma W into 1 minus n. So replacing this with the Gs into gamma W into 1 minus n, and you know the total volume over here. We took this, assume this equal to 1. So if you put this is equal to 1, so gamma D is equal to Gs gamma W into 1 minus n. So dry unit weight is equal to specific gravity times unit weight of water into 1 minus the porosity. So Gs is constant for a particular soil because unit weight of soil solids remain constant. So the specific gravity of soil solids remain constant. Unit weight of water is constant, 62.4 pounds per cubic feet. In the FPS system, if you are taking SI system, it's 9.81 kilonewton per cubic meter. If you are considering it as in kilogram, then you will have to take the density or rho W, and that will be equal to 1000 kg per cubic meter. So this is how you can develop a relationship between dry unit weight and these properties. Now we are going to go towards the bulk unit weight. Now bulk unit weight is unit weight of soil solids plus unit weight of water or total weight, okay, because total weight is made up of solids and water because air does not have weight. So WW plus WS is total weight. So bulk unit weight is basically equal to total weight divided by total volume. Now over here you can see that we have Ws once again is equal to Gs gamma W into 1 minus n. So replace this with Gs gamma W 1 minus n, and we also have WW, which is equal to this. Okay, now you can see over here, if you take this and this, if you put the values, you can see Gs gamma W into 1 minus n is constant in this. Okay, it's common, Gs gamma W 1 minus n. So we will take common Gs gamma W 1 minus n from both, so we will get Gs gamma W 1 minus n. We have taken this common, so in first one the remaining is 1, and the second one the remaining is W. So the relationship between the bulk unit weight and porosity, if you know the moisture content of soil, if you know the unit weight of water, and if you know the specific gravity, if these two are constant, this can be easily determined in the laboratory. And if you have porosity as well, then you can determine the bulk unit weight using this relationship. So bulk unit weight gamma is equal to GS gamma W into 1 minus N into 1 plus W, or bulk unit weight is equal to specific gravity times unit weight into 1 minus porosity into 1 plus moisture content. Remember, when you are solving numericals etc. in the coming lectures, this should be used as ratio. You will not put moisture content in terms of percentage in the equation. We will be solving equations in a while, then you will know that how we are going to use this. Now we have developed an equation for the dry unit weight and bulk unit weight. Now we are going to derive correlation or relationship for saturated unit weight. Now we know that when the soil is fully saturated, its saturation ratio is equal to 1. So all the voids are filled with water. This is our understanding. So all the voids will be filled with water. The water will be not up to here, but all this portion will be also filled with water. So the total volume of voids will be the total volume of water. So we know that from our previous equation, which we determined, structural engineers equal wacky guys previously. So SE is equal to W times GS. Now we know that S over here is equal to 1 because soil is fully saturated. In this case, we want to develop correlation for fully saturated soil. Now obviously for fully saturated soil, S is equal to 1 because S is equal to volume of voids divided by volume of water divided by volume of voids, and volume of voids and volume of water will be same over here because all the voids are filled with the water. So S will be equal to 1 as we discussed previously in the previous lectures. So E is equal to, or your void ratio is equal to moisture contents times specific gravity. Now we also know in the very first correlation which we developed is that your void ratio is equal to porosity divided by 1 minus porosity, or E is equal to N divided by 1 minus N. So in this equation we can replace the value of E using the right hand side of this equation. So if we put that and we keep GS on other side of the equation, we bring GS over here as well. So moisture content W will be equal to E divided by GS, while E is equal to N divided by 1 minus N into GS. So all this is in denominator. Remember, N divided by 1 minus N into GS. Now by putting the value of W in the equation for WW, which is this, okay, in this equation we replace the value of W from here, from this equation we take it N into 1 minus N into this equation over here. So if we put the value, so WW or weight of the water will be equal to N divided by 1 minus N into GS. Okay, we have replaced this into GS into gamma W into 1 minus N, which is GS into gamma W into 1 minus N. Now over here you can see 1 minus N and 1 minus N is common, so they will be cancelling each other. GS and GS is common, so they will be cancelling each other, and we are only left with N and gamma W. So weight of water will be equal to N times gamma W for fully saturated soil. Okay, for fully saturated soil it will be equal to N times gamma W. So we know in case of fully saturated soil, its unit weight is equal to weight of soil solids plus weight of water divided by the total volume. Now weight of soil solids, we already determined relationship for that. This is equal to GS into gamma W into 1 minus N. So GS gamma W into 1 minus N. And for the weight of water, we have just developed this relationship for fully saturated case, which is equal to N times gamma W. So in this equation, the gamma W is basically constant. So taking gamma W constant divided by the volume as well over here, which is equal to 1. You can see we assume this is equal to 1. So saturated unit weight is equal to 1 minus void ratio into specific gravity plus 1 minus porosity into specific gravity plus porosity into gamma W or unit weight of water, or 1 minus porosity into specific gravity plus porosity whole into the unit weight of water. So this is how we have developed the relationship between the saturated unit weight, porosity and moisture content, which you can see over here. The porosity, specific gravity, unit weight of water, correlated to the saturated unit weight of the soil. So in this fashion you can determine the number of relationships. I've given all the relationships on this table over here. You can see there are three important parameters which we always need: the moist unit weight or bulk unit weight, the dry unit weight, or the saturated unit weight. Under different conditions we require these for sake of determining the amount of water to be added, for making it fully saturated, or if the soil is fully saturated we need to know the dry weight of that soil. If we dry it, how much it will be, etc. If we know the water content of moisture content of particular soil, how much will be void ratio, if we know specific gravity. So we will always need all these relationships. So in this table you can see, if you have the properties which are available on the left, which you can see these, you can determine this quantity using these correlations. Okay, so for example, if you have moisture content Gs and E and you want to determine the moist unit weight, then moist unit weight gamma will be equal to 1 plus moisture content into Gs gamma W divided by 1 plus E. Okay, but if you have saturation ratio Gs and E instead of moisture content, now you got saturation ratio, so there will be no moisture content in this equation. You can see that will be equal to Gs plus Se into gamma W divided by 1 plus E. We have derived all these relationships in the previous slide. Similarly over here, if you want to determine the dry unit weight, so if these of the properties, these are available, any of these are available, you can use these correlationships to determine the value of gamma D. Okay, you can see the factors, the properties which are available on the left, they will be always in the equation. Okay, so on this table you can determine also for saturated unit weight. You can see over here, if these properties are available with you, okay, specific gravity you can determine in the laboratory. Similarly, I talked about void ratio and porosity and moisture content. They can be easily determined in the lab. So if you have these properties and if you want to determine the saturated unit weight, you will be using the following relationships for the saturated unit weight. So keep them with you, maybe they will be available to you in the examination as well. So you need to know that if the properties are given, you need to play around with these correlations and determine the required property, whether it's moist unit weight or bulk unit weight or dry unit weight or saturated unit weight. Some of the typical properties are given in the following, just in case you are wondering that you have a particular property available with you already measured and you know that this is relevant or not, or how much unit weight or void ratio or moisture content or dry unit weight you are expecting for a particular soil. So in case of sands, you can see loose and dense sands over here. If the sand is in loose form, obviously the volume of voids will be more, so the void ratio is high. If the sand is in dense form, the void ratio will be less. Similarly, you can see the natural moisture content. If the voids are more, there can be more moisture in that sand. If the voids are less, obviously there will be less voids available, so there will be less moisture content. Similarly, you can see the dry unit weights as well in terms of pounds per cubic feet if you are using FPS system. Similarly, you can see in the MKS system or SI system as well, you can see that if you compact, if the sand is compacted, then the unit weight will be higher, dry unit weight, and if it is in loose form, the unit weight will be lesser. Okay, so you will have higher unit weight for the more denser sands or for denser soils in common. Similarly, loose angular grained silty sand and dense angular grained silty sand, you can see over here. For that, more or less your void ratio and bulk unit weight density remains constant. Then you have clays over here. For stiff clays the void ratio is less, but if it is soft clay, the volume of voids are more. So sometimes the volume of voids are even more than volume of soil solids, so you can have the void ratio greater than 1 over here as well. Similarly, when there are more voids, there will be more moisture content as well, and there will be lesser dry unit weight as well. If the voids are less, the dry unit weight will be more. If the voids are more, then the dry unit weight will be less, of course, because we know the dry unit weight is weight of soil solids divided by the total volume. So similarly, talking about lowest or soft organic clay, you can see especially in case of organic clays or peats, their volume of voids are several times the volume of soil solids. You can see over here their void ratio is 2.5 to 3.2. So if we have a void ratio of soil having 3 void ratio, it means that it has 3 times volume of voids as volume of soil solids. So if there is 1 cubic meter of solids in this soil, then there will be 3 cubic meter of the voids in this particular soil. So they are very foamy, spongy soil. They've got a lot of voids, and similarly they can have a lot of moisture content as well. And similarly, vice versa, they have got very less dry unit weight. That's why they are problematic soil and they are not very good for construction, etc. On the other hand, glacial till, which we already discussed in the geological formation of the soil, they are also one of the heaviest type of the soil, which you can see over here. Their dry unit weight is highest of all, and their void ratio is also very less as well. So they are usually a preferred choice for the construction. We'll deal with them later on in the design problems. Now coming to some example problems to use these relationships to determine the properties or various conditions of the soil, the volume of voids, the volume of soil solids, the volume of water, the weight of water, the weight of soil solids, the weight of the soil in dry form, etc. These few things may be required. So for example, if you have a problem, example problem 3.2, we already solved 3.1 previously. So if you have, for example, there is a moist soil sample with the following properties given. We have moist soil. It means that it has moisture, it's not completely dry, moisture in the natural condition. They did not mention it's fully saturated, so we will not consider it to be fully saturated. Over here we will see that how much saturation it has. So the total volume of the soil is 1.2 cubic meter. The total mass of this soil they've taken is 2350 kilograms. The moisture content they have determined in the laboratory, which is 8.6%. And specific gravity they have determined also in the laboratory, which is 2.71. You can determine this using pacnometer, and this is easily determined using oven. This can be determined simply by weighing the soil, and this is the volume of soil, which is usually determined by measuring the dimension and using the volume. So determine the following: moist density, dry density, void ratio, porosity, degree of saturation, and volume of water in the soil sample. Now remember, over here they are asking about densities, not unit weights, and you know that your unit weight is equal to density times rho, which is represented as rho times gravity, okay, which is 9.81 meter per second square in case of the SI system, or 32.2 feet per second square in case of the British or FPS system. Now let's starting the solution, because obviously we require density. Over here the density is basically equal to mass per unit volume, and the mass should be in kgs if you are determining the density. If you are determining the unit weight, then the mass should be in the kilonewton over here. So always remember that, then this property should be in kilonewton. If you are required to determine the unit weight over here and you are given this in kgs, so you will multiply this by 9.81 and divide by 1000, and that will give you the total weight, not mass but weight. So the unit weight is weight per unit volume, and the density is mass per unit volume. The units of mass is kg and the units of weight is kilonewton. Okay, so moving on, your density is equal to mass per unit volume. The mass is provided 2350 kilograms divided by the volume, which is 1.2 cubic meter. So your density is 1958.3 kilogram per cubic meter. So we have answer to the first one, which is the moist density, part A. No, part B is determine the dry density. Now dry density is basically equal to the density or the mass of the soil solids divided by the total volume. Now you know that the total mass of the sample M is equal to mass of solids plus mass of water. Okay, so this is equal to that. So if I take from this equation, let me just write it. If I take from this equation ms common, so if I take ms common from this equation, so that will be equal to ms into 1 plus mw divided by ms. What is mw divided by ms? That is equal to moisture content. So the equation is ms into 1 plus w, or 1 plus moisture content, or ms is equal to total mass divided by 1 plus moisture content. So replacing ms, this ms, okay, mass of the soil solids, by this, okay, in this equation, because we have these properties. We have total mass, we don't have mass of the soil solids over here, but we have total mass and we have moisture content, and we have volume as well, of course. So this is why you need these relationships. So if you don't have a particular property but you have other properties which can give you that property, so you can replace it with those properties. So the total mass is 2350 kilogram divided by 1 plus moisture content. Now I told you that moisture content will be always in the form of ratio. Over here it is in percentage, 8.6%, which basically means 8.6 out of 100. So I will write 8.6 divided by 100. You should write it as a ratio when you are using it in equation, not as percentage. Always remember while solving the problem in exam that never use the moisture content as the percentage, but always to remove this percentage you will have to divide this by 100. Okay, so 8.6 divided by 100 into total volume is 1.2. So putting the value 1.2 over here, so the dry density is equal to 1803.3 kilogram per cubic meter. So you've got dry density as well, which is this. So this is check and this is check. Next is void ratio. So previously we derived equation for the dry unit weight GS and E, which was equal to gamma D is equal to GS into gamma W and divided by 1 plus E. Where was that? That was the equation for dry unit weight, which is this one. Okay, this is what we derived. If you've got GS gamma W divided by 1 plus E, we can determine the dry unit weight. So the same relationships can be used for the dry density as well, because we will be simply replacing gamma D by rho D into G, and this by rho W into G. So G and G will cancel. So instead of gamma you can write density or rho as well. So the same equations which you are using for unit weights, they can be used for density of the soil as well. For the relevant density, like from the dry unit weight equation can be used for dry density, the bulk unit weight equation can be used for bulk unit weight, and the saturated unit weight equation can be used for saturated density. The problem you should always remember that also on the right hand side you should be also using density, not unit weight. Okay, so from both sides you will change the gamma by rho, and you can use the same equation for the density as well. So we have this equation. Now in this equation we have got rho D, we've got GS, we've got rho W, which is constant. What we need void ratio. So keeping void ratio on this hand side of the equation, so taking void ratio over here and rho D divided by, and then there is 1 plus E as well, so taking 1 on the other side of the equation. So the equation simplifies to GS rho W divided by rho D, which is over here, and then minus 1 over here. So just putting the values into this equation, GS is given as 2.71 specific gravity, so that is already given, so we just put it from there. We know the unit weight of water is equal to 1000 kg per cubic meter, which is constant, so we just put it over here, and we already derived the dry density, so we take it from here and put it in this equation, minus 1. So the void ratio is 0.503. So third requirement is also check void ratio is determined, which you can see in the following. Now the next is about the porosity. You can see the porosity is equal to void ratio divided by 1 plus void ratio. This is one of the very first equation which we derived. So you can see over here, just putting the value of void ratio as 0.503, which we just derived on the previous. Over here you can see void ratio is 0.503, so 0.503 divided by 1 plus 0.503. So the porosity of this soil is equal to 0.335. so number 4, part D, which is the porosity. This is also checked, we have determined that. So what is next? We need to determine the degree of saturation, or S, which we can use the equation structural engineers equal wacky guys. SE is equal to W times GS, which we already determined this equation. So SE is equal to W times GS, while S is the saturation ratio, E is the void ratio, W is the moisture content, GS is the specific gravity. So SE, we take the E on the other hand side of the equation. So S is equal to W times GS divided by E. W is given in the beginning, which is equal to 8.6% already. Okay, so 8.6. GS is also given, which is 2.71, which you can see on this slide. So we're putting it 2.7, and E we have just determined it above, which you can see over here. So just putting it in this equation. So in solving, you get 0.463 as saturation ratio. You can write it as 0.463 as well, or 46.3 as well. It's up to you. So 46.3% means that 46.3% of the voids are saturated with water, while remaining of the roughly 53.7% of the voids are filled with air. So the soil is not fully saturated in this case. From this we know. Now coming to the part F, which is the volume of water in a soil sample. In this soil which we have taken over here, 1.2 cubic meter, having this much weight, how much is the volume of water? Now for this we know the volume, the density is equal to mass per unit volume. Okay, so the volume will be equal to, or volume of water will be equal to the density, mass of water divided by density. Okay, because we know that the density is equal to mass per unit volume. So shifting density over here and volume on this side of the equation. So volume of water is equal to mw divided by rho w. Now total weight of water is equal to total weight minus weight of solids. Okay, so if we subtract the weight of solids from the total weight, we will get weight of water in a given soil. Now we already know, we derived on the previous over here, that ms is equal to m divided by 1 plus w. So replacing ms is m divided by 1 plus w, where w is the moisture content and m is the total mass. So we know the total mass is given to us 2350 kilograms, okay, into 2350 once again divided by 1 plus moisture content is 8.6%, which we should write 8.6 divided by 100 over here, and density of water is constant, which is 1000. So just putting the values into this equation, so 0.186 cubic meter. So in this soil sample which we have taken, the total volume is 1.2 cubic meter, and in this 0.186 cubic meter is the water. Okay, and the remainings are basically the voids and the solids. So volume of water is equal to this. This is the alternate solution of the same problem. I have just left it for you guys. You guys can try it yourself, see if you can determine, if you remember from where the relation is coming and how this is being solved. So this is the alternate solution. There is not only one relation, there are a number of relationships over here which you can use. So you can determine one properties using several different methods over here. So you can see part A, which is the bulk density is determined over here, which is the same procedure. Part B, same procedure has been adopted for the dry density, while part C and onward they have used different approach. Okay, because one property is related to other properties in number of manners. So over here they have determined every property and then measured like porosity, calculated porosity by actually dividing volume of voids divided by the total volume. So they determine volume of voids and total volume is already given, so they have determined this. And simply, so just try it yourself and give me a feedback in the live Zoom session and see that if you can solve it If you have any questions, we will discuss that. Now coming to example problem 3.3. Over here the following data are given for a given soil. The porosity is 0.4 given. Specific gravity of soil solids GS 2.68, moisture content 12%, so there is 12% water. Determine the mass of water to be added to 10 cubic meter of soil for full saturation. So we have this soil available with us, which is the volume, total volume is 10 cubic meter, and its moisture content is 12%, specific gravity 2.6%, 2.68, and the porosity is 0.4. It is asking that its current moisture content is 12%. How much water you should be adding? Okay, the mass of water, not volume. They are asking about the weight of water to be added to make it fully saturated. So all the voids will be filled with the water. Using equation 3.27 from your handouts, we already determined that density rho is equal to GS rho W into 1 minus N into 1 plus W. So basically the equation was determined for the unit weight, but in your handouts I have also given you the equation in terms of density as well. So if you don't know where it is, if I come back over here, because I am taking the bulk, so W, GS and N is known, so I can use this relationship to determine the bulk unit weight, which you can see over here. So because I am determining the bulk density, not unit weight, so this will be replaced with rho. Okay, so rho will be equal to GS into gamma W into 1 minus N into 1 plus W. This gamma W will be replaced by rho W, because I am using rho or density on the left hand side of the equation. So if you are using weight on the left side, then on the right side you have got weight. If on the left side you have got density, then on the right side you should be also getting density of water, which is rho W. So this is the equation I am using over here. So you can see over here, rho is equal to GS into rho W into 1 minus N plus W. So instead of gamma W, I am writing rho W, because I am also writing rho or density over here. So density on this side of the equation as well. Okay, so remember the density is in kgs and the unit weight is in kilonewton. Similarly, from equation 3.28, we know the saturated unit weight is equal to 1 minus N into GS plus N into rho W. So in terms of density, I have provided this equation in terms of unit weight, so you can determine vice versa. This is the equation which I am talking about. You got GS and N, and you can determine the saturated unit weight using this equation. So if you want to determine saturated density or rho sat, then you will have to write rho sat is equal to 1 minus N into GS plus N into rho W. Okay, so this equation you can see into rho W. So over here, if we have the bulk density, if we also have saturated density, then we subtract them from each other, we will know that how much density or how much water is to be added per unit, per cubic meter, and we will multiply this with total volume. So first of all, in the existing condition, how much is the density? So from this equation we can determine that. Now GS is 2.68 given, rho W is 1000 kg per cubic meter, which is constant, into 1 minus your porosity N is 0.4 into 1 plus your moisture content is 12%, which is 12 divided by 100. So because you will be always writing this in terms of ratio, so 12 divided by 100. So bulk density is 1800.96 kg per cubic meter. So under this percentage of water, its density is this much. Okay, now how much should be the density if it is fully saturated? For that we need saturated density, so we use this equation for the saturated density, which is equal to 1 minus N into GS plus N into rho W. So 1 minus N, which is 0.4, into GS, which is 2.68, plus N, which is 0.4, into rho W, which is unit weight of water, which is equal to 1000. So the saturated density is 2008 kg per cubic meter. So we know that how much will be the difference made by the water if it is fully saturated per cubic meter by subtracting those two. So saturated minus bulk density, that will give you that how much is the difference in terms of weight of water between saturated and the bulk sample, okay, or sample under normal condition. So per cubic meter, that much kg difference is there if the soil is fully saturated. In 10 cubic meter, you multiply this by 207.4 multiplied by 10. So in 10 cubic meter of the soil, you should be adding 2070.4 kilogram of water to make it fully saturated over here. Okay, so by this you can determine that if how amount of water to be added in a particular soil to be fully saturated, or how much water this soil will take to become fully saturated, etc. So you can determine the capacity of a particular soil from this to absorb the water. So this is required in various hydrology problems as well, and various retaining wall stability problems or foundation problems as well. Sometimes you require this. So, and also in the fill and borrow problems as well. So it's also very important. Another short example, and then we will conclude. Example 3.4. A saturated soil has a dry unit weight of 103 pounds per cubic feet. Its moisture content is 23%. Determine the saturated unit weight, gamma sat, specific gravity Gs, and the void ratio. So you got the dry unit weight, gamma D, and you got the moisture content W. Okay, you require gamma sat, required specific gravity Gs, and you require void ratio. So first of all, determine gamma sat. Now if we go to the gamma sat equation, remember we have dry unit weight and moisture content with us. Okay, so if I want to determine the saturated unit weight, and if I have the dry unit weight and moisture content, which is over here, you can see I can use this equation. Okay, so gamma D into 1 plus W. So we can use this equation over here, which is gamma sat is equal to gamma D into 1 plus W to determine the saturated unit weight. So gamma D is 103, which is already given, pounds per cubic feet, into 1 plus moisture content is 23%, so I will write 23 divided by 100. Okay, so that is the moisture content, and this is given already over here, so just putting the values. So just solving this, your saturated unit weight is 126.69 pounds per cubic feet, or you can round this to 126.7 to a one significant figure, so 126.7 pounds per cubic feet. So gamma sat is known. Now the next is specific gravity. Now for specific gravity, we will use the correlation or the relation between the dry density, specific gravity, and void ratio over here. Now because we don't know the void ratio in this equation, we want to determine this. There are two unknowns over here, because for fully saturated soil we know that S is equal to S into E is equal to W times GS. Structural engineers are equal to wacky guys, as I discussed earlier. No, such fully saturated soil, then S will be equal to 1, so E will be equal to W times GS. Okay, so you can replace this E with W times GS in this equation and get this equation. Okay, so gamma D is equal to GS into gamma W divided by 1 plus W into GS. Because we have got W, moisture content, we have got GS, unit weight of water is known, we don't have void ratio yet. So in this equation we need to replace this. So gamma D is equal to GS gamma W divided by 1 plus W into GS. Now putting the values into this equation, gamma D is 103, GS we want to determine, this is unknown. Okay, so into unit weight of water over here, because we are doing an FPS system. Remember, you should always remember the unit weight of water in both systems on your fingertips. So in the FPS system is 62.4 pounds per cubic feet divided by 1 plus moisture content, which is 23%, so 23 divided by 100, so 0.23 into GS. So solve this equation for GS and you will get GS is equal to 2.66. So the specific gravity is determined over here as 2.66. Now the next is void ratio. So we will use the same equation over here. S into E is equal to void ratio, but S is equal to 1 over here because soil is fully saturated. So E is equal to W into GS. W is 23 divided by 100, which is 2.3, okay, which is already given over here. So 23 divided by 100 because it's a percentage, multiply by GS, which we have just determined in this equation. So by putting this equation and solving, we can get the void ratio. E is 0.61, so void ratio is also determined as well. So there are a number of other numerical problems which are provided in the practice problem section or in the end in the exercise section of the textbook. You can try them for yourself and see. Don't get confused by having too many correlations over here. If you know the three-phase diagram, if you know how to determine the density from unit weight or unit weight from weight and volume, etc., and you know the basic of the unit weights, like what is saturated unit weight, which is dry unit weight, what is bulk unit weight, or what is saturated density, what is bulk density, and what is dry density, and what is unit weight of solids, what is GS, etc. You can easily determine these correlations. So it will not be a problem. Hopefully, still, if you have any questions and queries when we are in live session, please do ask the questions, because in next class we will be moving to the next topic, which is relative density of granular materials, which is also a very important topic. So we will discuss that inshallah in the next week, in the next class. Till then, take care. Thank you for listening.